Maurizio. So, Matteo, maybe you can start recording the seminar.
Yes.
Okay, so good afternoon, everybody. It's a pleasure to have you here, and it's a pleasure to have Maurizio Giannotti today with us. Let me briefly introduce you to Maurizio. Maurizio got his PhD at University of L'Aquila, so very close to us in Abruzzo, to Teramo, in 2002. And then he moved to Ferrara, at University of Ferrara, where he worked until 2006. And then he moved to the Los Alamos National Laboratory in New Mexico and US until 2009. And since then he's a professor at the Barry University in Miami, Florida. During these years, Maurizio has been involved in research on various aspects of high energy physics, astrophysics, and cosmology. And in particular, since 2015, he's been part of the Axions International Observatory. I don't want to pronounce the acronym. I'm afraid I may be wrong, which is an international group with the aim of building the largest helioscope for searching axions from the sun. So, I guess that we will hear about this later, and Maurizio will certainly give us the right pronunciation. And again, it's a pleasure to welcome Maurizio, and today he will talk about news on the astrophysics of feebly interacting particles. Maurizio, I'll leave you the microphone, and please everybody mute your microphone, and I'll give you the 40 minutes time.
Okay. Thanks. So thank you so much. It's a pleasure to be here. I want to thank very much Michele and Oscar for inviting me to give this seminar. So here I want to discuss a little bit some news about the astrophysics of feebly interacting particles, and by news I mean some results. I especially want to focus on some results that are very new, from mostly from 2020 or close, right? And let me just first clarify a little bit. So first of all, I will mostly talk about axions, really almost entirely. So by feebly interacting particles, I mean, for this seminar, I pretty much mean axions, even though what I say in this talk will apply also to other feebly interacting particles, and I have backup slides in case we want to discuss see some other applications. Okay, but for reason of time, I will focus on axions, which are certainly some of the most interesting among the feebly interacting particles. And the talk is divided in two parts. So in the first part, also we'll talk about stars, right? So for astrophysics, really means stellar astrophysics in this talk. And I will focus in two parts. In the first part, I will use stars as laboratories. So I'm going to look at how the evolution of stars can be modified by feebly interacting particles, right? And so we can test feebly interacting particles from the observations of stellar evolution. And then the second part, which is the longest and perhaps even more interesting, I don't know. I will look at stars as factories for these feebly interacting particles. So I want to see if we're actually able to detect stellar axions. So what's the status on that? Okay, so first of all, there is certainly a growing enthusiasm in the physics of the light weakly interacting particles, which, notable examples are neutrinos, axions, right, dark photons, and all that. And the interest is due to the fact that new physics may be hiding there, actually, at the low energy frontier. And because these particles emerge in theories which extend the standard model and explain some of the issues with the standard model, such as the origin of dark matter, or the nature of dark matter, etc. Right? And there are many initiatives, new initiatives like Physics Beyond Collider and discussion about the Feebly Interaction Particle Physics Center, now at CERN, where for young students, for young researchers, maybe opportunities to work in this field of the low energy frontier, which I find it very interesting. Okay, so let's start with axions. Axions in a nutshell. I want to just give you some brief information. So axions are pseudoscalar particles. They're spin zero particles. They were introduced to solve problems with the strong interactions, in particular with the symmetries of strong interactions, which are observed to preserve CP symmetry or time symmetry. But then, you know, theoretically, it's not easy to understand why this preserves the symmetries, and axion emerges in the Peche-Quinn solution to this problem, okay? So, but for us, this is a phenomenological talk. For us, what's interesting is that the axion is a pseudoscalar particle that couples to standard model fields. I hope you can see my cursor here, all of you. So for me, from a phenomenological point of view, what's very interesting is that actually we can see axions, right? Because axions couple to fermions, so electrons and nucleons, and to photons, okay, through these couplings here, okay? And then they are expected to be very light, sub-eV, in most scenarios, but they can still be cold dark matter candidates because they are non-thermal production mechanisms. And I will not discuss the cosmology, but it's good to know that they're excellent dark matter candidates. Okay, so there was a recent review where we discussed a lot of these things. So now let's look a little bit at the parameter space, because I will use a lot this to somehow describe the phenomenology. I will use a lot of the parameter space. So the parameter space is made normally with the mass on the x-axis and one coupling on the y-axis, okay? So and often we choose the coupling to photons, and the reason is that the coupling to photons is the most well-studied experimentally. Okay, so this is a good section of the parameter space. You know, all the parameters above 10 to the negative 10, GV to the negative 1, coupling to photons, yeah, these are excluded. So okay, so the bottom part is the one that we need to explore. So there is a region here which is this yellow band, and this is where axions, so the models for axions that actually solve the strong CP problem, right, tend to have parameters that are in this region. So they tend to have a coupling that's proportional to the mass, right, within some range. And this region was discussed in this interesting paper by our Italian collaborators, right, Luca Di Luzio, Federico Mescia, and Enrico Nardi. So the region outside this band is often associated to axion-like particles, or ALPs. So these are particles that don't necessarily solve the strong CP problem, but still they have the same phenomenology of QCD axions, right? So for me, in this talk, this distinction is not very important. So I will always talk about axions, right? And the phenomenology is similar from what I say. So I will always talk about axions and whether we're here or not. So this was just a clarification. So let me mention also that this parameter space here is largely unexplored now, experimentally. There is only a little bit of this area here was excluded, and then a little bit of area here is being studied. But the experimental perspectives are fantastic. So without going into the details of the experiments, some of them I will mention later. So the next generation, meaning the 2020s, right, we'll see a large exploration of this region. So there is a lot of enthusiasm, certainly, for this study. Lots of sensitivity studies for new experiments, which will cover pretty much all of this region, okay? Which is very exciting, very interesting review here in this paper, okay? So now we get to stars, right? Because so the problem is testing experimentally weakly interacting particles is very difficult because they're weakly interacting, right? So the fact that they interact very weakly make it very difficult to detect them. However, stars are very good at studying these particles. And in fact, this is a very old paper that I found a number of years ago. 1963, right? These scientists studied the electromagnetic properties of neutrinos, in particular the neutrino magnetic moment, from the sun. So in 1963, so this is like 60 years ago. So evidently they're excellent laboratories, right, to study these particles. So why is that? The reason is that for stars, Feeble is good, right? For an experiment, Feeble is bad. But for stars, Feeble is good. Why? If you have a strong interacting particle here, CP, strong interacting particles can be produced in the sun, or well, in a star, in any star, right? Because you have a thermally produced, right? You have a plasma, hot plasma. You can produce these particles. And then this particle, transport energy very inefficiently, right? Because they scatter a lot, and then they're emitted from the surface. Now, if you have a Feebly interacting particles, okay, maybe the production may be a little bit suppressed, but then when they're produced, they export energy extremely efficiently because they don't re-interact in the stellar plasma. Okay, so when you look at the emission rate, you have a curve like this, right? So with increasing coupling, eventually you get worse and worse, and eventually you go to a black body emission from the surface, right? So there is a sweet spot where you can actually study fairly feebly interacting particles better in stars than you would photons, for example, or, particles that are strongly interacting. So there are two consequences of this. One is that these particles may be very efficient energy loss, and therefore they modify the evolution, and that's part one of my talk, right? And then the second, that you have a large flux, and so maybe we should look at these particles that are produced in this way, right? So that's what I want to focus on. So the first part, I will go a little bit quick because I think you're all experts on stellar evolution. I don't want to repeat things. There are several observables in stellar evolution that may help constrain the new physics. So especially efficient energy loss. But when we look at stellar evolution from a particle physics point of view, it's always good to look at the core besides the surface, right? We observe the surface, but it's always good to take a look at the core because these particles are produced often in the core, right? So we start. A star at the beginning of the evolution is a main sequence, burning hydrogen in the core, is relatively low density and low temperature, okay? Then when the hydrogen is exhausted, it moves to the red giant branch over here, so it should be this one, right? And then it moves in this direction, so the density becomes larger and the temperature becomes larger. And eventually the helium core ignites, and this is what's called the helium flash, and you're here. You're at the tip of the red giant branch. So this is already a good point, a good test. The position of the tip is a good test for new physics, because obviously if there is an additional cooling, this flash is delayed, and so the star goes to higher luminosity so it goes higher luminosity, as we can see here from this simulation from View et al. In 2013. Here they're assuming a new physics in terms of a neutrino magnetic moment, larger and larger. When you increase the size of the magnetic moment, the actual tip of the branch moves. Okay, so this is one possible test of new physics, which is widely used to test axions and other light particles. Then when the helium is ignited in the core, the star moves to the horizontal branch. Okay, so the temperature becomes a little bit higher and the density considerably smaller, right? And then when we look observationally, right, we can count stars in the HB branch and stars in the giant branch, and this ratio also is a test of new physics. Why is that? Because when we have an additional cooling in terms of new particle that's produced in the core and carries energy away, well, this emission rate may depend on the plasma, and in general it does. So it may be more efficient, for example, in the HB than in the RGB. And therefore, these parameters may actually measure, will give us information about the efficiency of the cooling and so about the particle. And finally, the star evolves, and eventually a LOMA star goes into a white dwarf. And we know that white dwarfs are stars that are only cooling, so there is not energy production, there is no nuclear reactions going on. So obviously, as a cooling star is ideal to study cooling, right? Remember that a lot of these constraints or these tests for new physics are based on the fact that axions and other light particles tend to carry energy away, right? So for a white dwarf that's just a star cooling, well, seems to be an ideal place to study additional cooling, right? In fact, you would describe the cooling with an additional piece, which is the energy loss in this additional particle, the axion, for example, right? And in fact, if you plot the distribution of white dwarfs per luminosity bin, the so-called white dwarf luminosity function, well, this curve tells us a lot about new physics, right, in terms of axions or other particles. In fact, this is one of the most interesting observables because it can also distinguish, the shape of this line can also distinguish between among different kinds of additional cooling. Finally, one last observable is the period change of white dwarf variables. So some white dwarfs are variables, meaning that their luminosity changes periodically. The periods are order of minutes. This period changes very, very slowly, and this change of period is a measure of the efficiency of the cooling. Okay, so it's very difficult to measure the periods change. It takes decades. That's what I was told by the experts. It takes decades. So we have in a few cases, this period change has been measured, and it's interesting that in all cases there is a sort of a little bit of tension between the observed and the predicted period change, which tend to indicate the need for additional cooling. So later on this, a little bit later, okay? So let's now go to axion, right? So what does axion have to do with this? Well, axion can be easily produced in stars, and therefore contributes to the cooling or to the energy loss in general of stars, and therefore we can use those tests to look for axions, signatures of axions in stars, right? So let me mention that the primary mechanisms for axion production in stars are the Primakov, which is the conversion of a photon into an axion in the electric field of a nucleus, ions, right, or electrons. Then we have the Compton and the Bremsstrahlung. So the Primakov tests the coupling to photons, axion coupling to photons, and these other two tests axion coupling to electrons. So here, this is a picture of the plasma density, temperature, and the relative importance of these mechanisms, production mechanisms here. These numbers indicate our contour lines for the energy loss in ergs per grams per second for certain couplings here. So as a rule of thumb, this region, which is the non-degenerate region, is a very efficient. In this region, the Primakov is very efficient. So normally we find the best bounds on the axion photon coupling looking at stars in this region here, upper left. And then we find the best bounds for axion electron coupling in this region here, because in this region the Bremsstrahlung is very efficient, so in the degenerate region. Okay, so let me mention that there are other possible mechanisms here that I'm not mentioning. One particularly interesting is the possibility of axion produced from a photon conversion in the magnetic field of stars. This is a relatively new idea. It's been studied particularly well in this last year. There have been a few papers, which I will not consider because of reason of time. It's hard to be to explain everything, right? So, but you can look at this reference. It's very, very interesting and still work in progress also here. So if we now put everything together, we find bounds on these axion couplings from the tests that I discussed before. So not surprisingly, the best bounds on the coupling with photons are coming from stars that are low density and high temperature. So we can look at the sun, for example, right? The sun is as a core, which is low dense, non-degenerate. But the bounds from the sun, in spite of us knowing the sun so well, the bounds from the sun are not as good because the sun is cold, is relatively cold. Best bounds come from horizontal branch stars, which are about 10 times hotter in the core than the sun. Okay, so these are the best bounds are from 2014, 2015. Okay, also some bounds from massive stars in the blue loop, but something I will not discuss either, right? So if you look instead at the coupling with electrons, then the best bounds come from stars that are very dense with a degenerate core. So white dwarfs and RGB, red giant branch stars, the tip of the red giant branch. So these are equivalent. All these stars are fairly equivalent, in my opinion, as laboratories for stars. The best bounds are from the red giant branch, and that's because the last studies were done with the red giant branch. There have been two papers, independent papers, one from Francesco Capozzi and Jörg Raffelt, one from Oscar Straniero and collaborators, including me and some of you that are following. And these two are very, very equivalent, completely equivalent bounds, but independent. Okay. So let me just conclude this part by pointing out that if we do a study of all stars that I mentioned, all the criteria, all the tests that I discussed before, right, from stars. We see that in terms of axions, right, if we do a global study, we see that stars actually like a little bit of action. Like they prefer to have a little bit of action than to have nothing. Okay, so in fact, from the latest analysis, it seems that they exclude the zero coupling to electrons by about 3 sigma or something. So this is not a very strong, obviously, very significant hint, but still, it's interesting that the stars like a little bit of action with a coupling. This is the best point, right? With couplings that are not that small. So this is 10 to the negative 13, and then this is 0.2, 10 to the negative 10 GeV minus 1 in terms of couplings. These couplings are not that small with respect to the present technology, detection technology. So these are experiments that are planned to be running soon. And so they can have access to these couplings. Depending on the model, it may be difficult, but in principle, they have access to these bonds. So this is very interesting because next generation of axion scopes may be able to see if really axions exist and really help stars cool a little bit more efficiently. Okay, so now that I discussed how stars can be used to constrain the physics of axions, I want to ask another question. And the question is, can we actually see stellar axions? So this to me is very, very interesting because now we have technology that allows us to, we're very good at detecting these particles. So what can we learn from stars, right? Stars are fantastic factories for axions. So can we actually look at them? And this is a little bit newer as topic, right? But let's look at the sun first. So of course, we want to start from the sun. The sun is very close. We know it well. And so it's the first place to start, right? So the spectrum axions are produced in the sun, of course, and this is the spectrum. The main production processes are the Primakov, which I discussed before, which is depends on the coupling to photons, and then this ABC process. ABC stands for A is atomic, some atomic processes. B is Bremsstrahlung and C is Compton. Okay. So you have this spectrum expected of axions produced from the sun, which is picked at a few keV. So if we do a little bit of a back on the envelope estimates, we find that the sun produces about 10 to the 39 axions per second. That's a pretty large number. This means 10 to the 11 per centimeter square per second axion on Earth. And this is assuming couplings that are allowed now, right? But barely allowed. So this is somehow this number, this is an interesting number. This 10 to the 11 axions per centimeter square per second is what we are able to see now, pretty much now. Now, in the next 10 years, we can do better than that, right? So 10 to the 11 is a number that we definitely is definitely appealing. It's definitely something we may be able to see, even a little less than that flux, okay? So there are two ways to hunt for solar axions. Okay, so one is to look at axion conversion into photons in a laboratory magnetic field. This is called the CKD helioscope. And the typical example is the CAST, this would be the CERN Axion Solar Telescope. Okay, so what we do here is this. We look at the sun. The sun is producing axions. These axions come to the Earth. They're converted into photons in a magnetic field. And then and this would be X-ray photons, keV photons. And then they are focalized in a detector and detected. Okay, so this is the CKD telescope. And here we have the perspective, the future perspective, when we have this IAXO, which is what Michele was mentioning before, the International Axion Observatory. well, the IAXO will be able to use this technology to probe a large section of the unexplored parameter space here, this one. Okay, trust exists, and this is the bound. This is the prediction from IAXO. Now, very interestingly, there is a scaled-down version of baby IAXO, which is IAXO, which is called baby IAXO, and this is actually approved. This will be constructed in DAISY in Hamburg, and there was this year a conceptual design paper on baby IAXO. And the sensitivity estimate is this one. It's very good. It's very good already, and we'll be probably taking data in the early 2020s. So that's very exciting. Now, the second possibility is to detect solar axions, is to look at the axion electric effect. So the axion electric effect is the analog of the photoelectric effect. Okay, but with axion instead of photon. Okay, so this is the technology adopted by the large underground dark matter detectors, such as LUX and Xenon 1T, etc. Right? So the cross section, if we look at the cross section is related to the cross section of the photoelectric effect. So, for example, it's very convenient to use high Z materials, right? It probes the axion coupling to electrons, but there is a very bad penalty to pay in this case. There is this suppression of E over ME squared. Remember that E is over the keV. So this is a very large suppression. So these experiments are less efficient at this stage, right, to probe axions. Then there was, in 2020, you probably all heard about of the reported excess in the Xenon 1T. And these are the results. And so this was extremely exciting at the time. And in fact, the paper has almost 200 citations and stimulated a lot of interesting work, I think. So it was very beneficial, I think, a lot of interesting work. So the excess, they observed this excess over background. So there was some noise about being solar axions, because the axions actually do fit really amazingly well. Okay, so this was somewhat exciting. Unfortunately, it's very difficult to believe that these are solar axions. In fact, we definitely think they are not solar axions. The reason is that because what I told you before, right? If I superimpose the coupling required to explain this excess by Xenon 1T over what we learned from other stars, it's what I showed before, and we're very far. So it's several sigmas out. So it's very difficult to think that these are what Xenon 1T observed are solar axions. So this was explained actually in a paper also in 2020. However, this doesn't mean that this is not a new physics, right? It could still be new physics. They could still have seen axions actually, just probably not solar axions, probably dark matter axions or something else. So a lot of excitement. Could be other things, could be maybe hidden photons or something else, right? But definitely not solar axions. Now, what about other stars? So the sun, fine. We know it is over there. Now, other stars. I can look at main sequence stars, right? If I look at a star of the same kind of the sun, it doesn't make much sense, right? Because the sun is close. So why would I look at another star? The closest star is 4 light years away. It's too far. So it doesn't make sense to study a star that's similar to the sun, right? So we can exclude these main sequence stars, right? But then we know that the production rate of axions, it's very sensitive, right? Steep function of the temperature. So why don't we look at massive stars? What can we learn from massive stars? Massive stars are 10 times hotter than the sun. So, we gain a lot from the temperature there. And, it's worth looking at something, right? So let's do some example. This is a simulation of Betelgeuse. Okay, this is a simulation of Betelgeuse at different stages of the evolution. Okay, so the axion would be produced in Betelgeuse, in a massive star, with this spectrum. This is the production spectrum. So the spectrum depends on 3 parameters: a normalization factor, C, average energy E0, and an index, spectral index factor, which is beta. So we have 3 parameters, right? So now let's suppose that we actually have the axions exist. We have an axion telescope where we're excellent at detecting axions. We look at Betelgeuse with the photon telescope, right, and with an axion telescope. So when we look at the Betelgeuse with the photon telescope, we see that the surface. So obviously photons come from the surface. The surface of Betelgeuse doesn't change. So look at this. This is the evolution of Betelgeuse, different stages. Okay, and if you look at the effective temperature and luminosity, they don't change. So looking at Betelgeuse now, it's very difficult to know in which stage it is. We only know that at least past the helium burning stage, so it's not in main sequence. Fine, but besides that, we cannot say much. We cannot say how soon it will explode, for example, right? Because the surface properties don't change much. If we were able to look at Betelgeuse with an axion telescope, well, that would be fantastic. These things change so much, they're very sensitive to the stage. Why? Because axions are produced in the core, and the core is actually changing. So what we need is an axion telescope to look at massive stars, not photon telescope, right? Okay, so we don't have that though, right? Very unfortunately. In fact, though, let's just do some estimates before calling it out, right? Imagine we want to see if we're actually able to see axions from Betelgeuse, right? So this is the spectrum expected from Betelgeuse, okay, at a certain stage, right? So a back of the envelope estimate gives 10 to the 45 axions per second produced in Betelgeuse. This is a lot more than what is produced in the sun, okay? And they have picked 100 keV, so these are axions from Betelgeuse. However, Betelgeuse is 200 parsec away. So I lose a lot from the flux, from obviously the flux is divided by d squared. 200 parsec is a lot more than the distance from the sun. So I get only 1,000. So what I expect is 1,000 axions per centimeter squared per second from Betelgeuse. So this is too small, way too small. Remember I told you that we're able to see perhaps 10 to 11 axions. Well, 10 to 3 is too little. So that's a real shame, because we're not able to see axions from Betelgeuse, so we're not able to study the evolution of Betelgeuse with an axion telescope yet. All right, but we could do a compromise. So this is something I find very interesting. So we can do a compromise. So axions could transform into photons in the magnetic field, in the galactic magnetic field from here to Betelgeuse. All right, so now what happens? The probability, the conversion probability is given by this formula. Okay, so this is just a formula. But let's look at this formula. There is a d squared here in the conversion probability. So, and then there is this term, which I will ignore for now. So this d squared cancels the 1 over d squared that you get from the flux. And then you have a 10 to the minus 6 here, 8 10 to the minus 6. So this is 10 to the negative 5. So this is fairly large. This is not small. Imagine that I multiply this by 10 to the 45. So I multiply this by 10 to the 45. G11 can be up to 6.5. So this is large. So we get a lot. We can get a lot of photons if we're able to convert them. And photons are very easy to detect. And also the D drops. The distance drops. Okay, so we don't pay the penalty. We don't pay the penalty of being far. So okay, so but let's look at this a little bit better. So unfortunately, this term here, which describes the coherence of the oscillation, is a very high price to pay. Okay, because this term here forces, in the case of Betelgeuse, forces us to look only at masses below 10 to the negative 10 electron volts. So it forces us to be a very low mass. Now, so if you're willing to look, if we believe the axions are really very low mass, like less than that, then we have a large flux, very large flux, okay, of photons. Why? Because this then drops, this will be 1, okay, and the distance drops. Okay, so in general, we can look at Betelgeuse with a X-ray telescope, right? And we can look at axions produced by Betelgeuse with an X-ray telescope. Okay, so this and find a large flux, very large flux. Okay, so we did that. We actually requested we asked for a NASA grant, which we were awarded, and we decided to look at Betelgeuse with an X-ray telescope to look for axions. All right, so a real dedicated observation. Okay, so and as a telescope, we chose NuSTAR, and the reason is that it's the only telescope that we have now that can probe the very hard X-ray spectrum. Right? Remember that we need around 10 keV of energy, right? Sorry, 100 keV of energy. So we need NuSTAR was the best telescope we could use. So the NASA grant was written with collaborators from MIT, Sherstein, and Caltech, Brian, and then with Oscar and Alessandro from Italy. So it was this collaboration. And then we did the measurement, and we found no significant counts above background. So we didn't see axions, which is a shame because obviously, well, it would be better now to present this. So even without seeing any background axion, background, signal above background, we were still able to probe a region of the parameter space that was not probed before. So you see, our result is this. So this is the parameter space that I showed before. So our result is this, is from here to here. So what we were able to eliminate is this region, and there is uncertainty. Why is this uncertainty here? Because first, we don't know very well the magnetic field. We have uncertainty on the magnetic field, the size of the magnetic field. And also, we don't really know what's the stage of the evolution of Betelgeuse. And so we cannot have a correct prediction. But that was still an interesting result, okay? So finally, I want to look at one last, and this will be, for the last 10 minutes, this will be my last star that I want to consider. And these are supernovae. Obviously, as I told you before, I want to look at stars that are very different from the sun, right? Because the sun, if a star is similar to the sun, then the sun is the best because it's close. But supernova are actually superstars, right? These are extreme environments. They have a density of 10 to the 14 grams per cubic centimeter and temperature of 30 MeV. Okay, so very extreme environments. So axions can be produced in a supernova through these three mechanisms mainly. So Primakov, again, this is coupling to photons in the electric field of protons. Okay, so you have protons here, photon becomes an axion. Okay, then we have Bremsstrahlung, nuclear Bremsstrahlung, so two nucleons produce an axion. And then we have this last process, which is a negative pion produces an axion scattering of a nucleus. So this one is a very interesting process because it was only recently in 2020 that Bryce Fore and Sanjay Reddy discovered that there is enough pions in a supernova to make this process actually dominating over the others. So okay, so this was, I think, a breakthrough result in the physics of supernova axions from 2020, right? So the pion abundance was always underestimated before. So now this, as I said, this result was used then by Pierluca Carenza and others to actually show that this process may be dominating over the others. And something that's also even more interesting is that the axions produced through this process have a much harder spectrum, so this would be this spectrum here, than axions produced through the other processes, okay, which would be this one. So the harder spectrum makes it easier to detect them in Water-Cherenkov detectors because these axions are so energetic that could actually produce negative pions in a Water-Cherenkov detector. And this could be open a channel for detection, but this is a work in progress. Somehow it's something that has to be analyzed, but somewhat very interesting. This, I think, was a nice achievement of in the physics of axions, supernova axions from last year. let's do again some back of the envelope estimates. So we know how to calculate the number of axions that can be produced in a supernova using this general criterion by Rafelt, which is any new particle can carry away essentially just as much energy as the neutrinos. Pretty much, that's the point of the criterion, right? So we're talking about 10 to the 52 roughly ergs per second for 10 seconds in neutrinos and in axions. So in axions, this corresponds to about 10 to the 56 axions per second. So huge number. Now, if I look at Betelgeuse, Betelgeuse is 200 parsec away. Okay, so if I look at Betelgeuse, I expect something like 10 to the 13 axions on Earth from Betelgeuse per square centimeters per second. This is more than from the sun. So this is now we're talking about something very large, a very large flux. So can we detect this? Well, the problem is that this flux is short, so we cannot do a year observation or 3 years observations as we can do with IAX or other experiments, such experiments, right? But so it's very short. Not only that, there is another problem. This supernovae are rare. We cannot just decide today, we look there and we know that tomorrow there is a supernova explosion. So these supernovae are rare. And we don't have a lot of time to think about, right? Because the flux lasts 10 seconds or so. So we have to be very quick. So we know we need to know where to look. Okay? And so fortunately there was a very comprehensive, very, very nice work also in 2020. So another nice results of the 2020s. From this group of people, Cecilia Lunardini is Italian, and then some collaborators. And this was a very comprehensive study of the possible candidates, pre-supernova candidates. Okay, and we find that 31 candidates within 1 kiloparsec from the sun. Okay, so now let's look at this a little bit. So this pre-supernova, these pre-supernova candidates, supergiant stars, right? If they are in a late evolutionary stage, they can emit neutrinos. You know, after carbon ignition, neutrinos becomes relevant, right? You know, for the cooling of star. So you start producing thermal neutrinos and neutrinos from beta processes, and this emission increases with the time. So when you go to late stages, so we're talking about hours before the collapse. Maybe when you get to these hours before the collapse, you can have a significant flux of neutrinos, and so you can have a signal, and so then you can tell everybody, hey, look, in an hour or so, or 2 hours, or 4 hours, or maybe 10 minutes, there will be Betelgeuse will go off, or something else will go off, and so you can turn your telescopes. All right, so the problem is the angular resolution. And so this again, same paper from Cecilia Lunardini and collaborators, 2020. Very, very comprehensive study of the angular resolution problems. Okay, so we can use liquid scintillators to detect them and add some lithium compound to improve the angular resolution. But in general, this is I adapted from the paper the case to Betelgeuse, just to have a case at hand. In general, an hour before the explosion of Betelgeuse, we can expect to see enough neutrinos to have a signal, but with an angular error of about 15 degrees. All right, so this is where we stand. So I also noticed, so this asterisk here, I noticed that Betelgeuse is 11.6 degrees from another star, which is 280 parsec away. This is also a supergiant. So unfortunately, if we get the signal this signal, and we think maybe Betelgeuse could also be another star. So we have to still guess a little bit. It's a little bit annoying, but that's fine. This work certainly opens the door for proceeding in this way. But suppose we have the signal, right? So then once we have the signal, we can look at it with the telescope to see if we find axions. All right. So now, thank you. Yeah, thank you so much. I'm done soon. I'll be done. So now So how do we detect these axions? So one way to detect these axions is through their conversion in the galactic magnetic field. So what we get is photons. So one possible axion telescope is an actual gamma ray telescope. Okay, so we can look at axions using a gamma ray telescope. The best one we have is the Fermi Large Area Telescope so far for the energy range. Imagine, suppose that, consider that we are actually talking about photons of about 100 MeV or perhaps 200 MeV energy, right? So Fermi is definitely the best we have so far, at least as far as I know. So then, if you have an explosion from a galactic supernova, you get this bound here. Now, I will show you this in perspective, but this is an incredible area, a probed area. So you will be able to probe a huge area. I will show you in perspective later. Okay, and from Betelgeuse, something like this. Okay, so you can even probe non-galactic supernovae probably, but obviously with less precision. Okay. Now, another option, one of the problems, before I move on, one of the problems of this method, again, just like we saw before, is that you are constrained to be at low masses. Now, there was a very nice idea in 2020, again, last year, which would avoid this problem of constraint to be a low mass. And was this the idea of using a helioscope, for example, IAXO, as an axioscope. Okay, so one option is Fermi Large Area Telescope, as axion telescope from supernovae. One other was proposed last year is to use a helioscope, like IAXO, for example. Right? What do you do? Well, the proposal is just to turn it around and put here a gamma ray detector. And now, what you do, instead of using the galactic magnetic field, you use a terrestrial magnetic field, a laboratory magnetic field, the same that you have already in these helioscopes. Okay, this allows to probe masses up to 1 electron volt or so. So it's less powerful than Fermi. It's considerably less powerful, but allows to probe higher masses. And you would see a couple of events from Betelgeuse from using baby IAXO. Consider baby IAXO is already approved. Even 12 events for Spica, which is another possible supernova candidate. Okay, so when we look in perspective, and this I think is my last slide, so I'm done. So when we look in perspective, the possibility of detecting stellar axions, right? We have a cast. This is helioscope. So look from the sun. This is what you see from the sun. Next generation, baby IAXO, which will be running in early 2020s. You can move to this region here, so considerably better. Okay, then we have axions from supergiants. That's what we can do so far using new star. We could do better if we look at other stars, right? We could find stars that are in later evolutionary stages or something. But this is what we can do. This red line. Then for supernova axions is where we can do by far the best. Okay, for supernova axions we have this is what we can do if we're able to point Fermi Large Area Telescope to a galactic supernova while it's exploding. So this is fantastic. This area is huge. And then if we point a helioscope to a supernova exploding, we can probe this area. So this is still considerably better than what we know so far from the current axion helioscope. So it would be here up to here, about up to masses of 1 electron volt. Okay, so as I promised, I finished in time pretty much. So this is the conclusion. I want to mention that there are certainly strong axion bounds from stellar evolution, and this is a topic that's been studied for several decades. And we had new constraints in recent years, also last year, for example. There is also the interesting that the combined analysis of stellar evolution indicates some hints to axions in regions accessible to the next generation of axion experiments, which is also exciting. It will probably resolve these problems in the next 10 years or so. And then I discussed quite a bit the possibility of observing solar and non-solar axions. And I showed that you can actually probe, we have technology to probe unexplored region of the parameter space from also non-solar axions. What we need, and this is a comment that we can discuss later if you want, what we need is really to have a next generation of instruments for X-ray, for hard X-rays, so something that follows new star, and something that follows Fermi. There is not much in this, like at least as far as I know, in this energy band, which is 100 to 200 MeV for gamma, or 100 to 200 keV for X-rays, right? Or even 50 to 100 keV in X-rays. So certainly exciting times, many new results in 2020. I showed only a few, by the way. There were others, but I had to cut and I couldn't show everything. Okay, so I think the astrophysics and laboratory experiments may give us a definite verdict on axions soon. So stay tuned and thank you very much.